Okay. Next topic, the optimal growth model. I've got, what, about 40 minutes or so to get started on this.
Unpin.
Okay. So pinning the video doesn't really mean pinning the board. The pin falls out of the board apparently quite easily. Okay, so we want to go to a new topic now on the optimal growth model. We're ready to use the main results from stationary dynamic programming that we've been talking about over the last, what, 2.5 classes, to characterize the full solution path to this optimal growth model or neoclassical economy. Okay, so here's the way that I'm going to try to proceed doing this. What we're going to spend the rest of today talking about and into the next class on Wednesday is I actually want to derive some of the basic results in the context of a simplified version of the optimal growth model. I just call it canonical example. And the reason why I want to do that is because, well, there's two reasons. One, verifying the various assumptions is easier to do in this model because we have actual functional forms. But more importantly, in this canonical example, the policy function, that is the way the state maps into the control, can be derived analytically. That is, we can actually find an explicit solution for KT plus 1 in terms of KT, right? Like in the solo growth model, it was really easy to do, right? You can derive analytically the law of motion for capital. Well, you can also do that in the optimal growth model as long as you're willing to make certain assumptions about utility and production. That is, simplifying assumptions. In general, these models are not solvable analytically. You have to enlist the help of a computer to characterize the optimal policy function. Okay, so let's start with the easy example. Okay, so the example that I'm going to work with basically makes 3 assumptions. Here is the statement of the sequence problem. So here's what the benevolent social planner faces. She is going to attempt to maximize by choosing an infinite sequence of capital stocks and levels of consumption from date 0 to infinity to maximize the lifetime utility of the representative agent in the economy. So that's the sum from t is equal to 0 to infinity of the discounted value of utility. We're going to assume that utility is logarithmic in consumption. So that's the first simplifying assumption. We've got log utility. So those income and substitution effects that we talked about in the context of the OLG model perfectly balance out here, right? What is the resource constraint that the planner faces? Well, consumption plus whatever is invested in the capital stock in any given period cannot exceed what is actually produced in any given period. So the resource constraint here makes a couple of assumptions. First off, the production function in this economy is Cobb-Douglas. So output is equal to K to the alpha. So we're dealing with logarithmic utility and Cobb-Douglas production. But what is the other assumption we're making here? You'll notice that the capital stock fully depreciates every period. So delta is equal to 1. So investment then is just equal to next period's capital stock. So CT plus whatever capital we have to carry into period T plus 1 is whatever we produce today. Otherwise, we would have a plus 1 minus delta KT on the right-hand side of that constraint, right? But if delta is equal to 1, capital fully depreciates every period. So we consume and we devote resources to the production of capital, and that must be less than or equal to how much output we produce every period. So this is the resource constraint that the planner faces. It's not a budget constraint or an income constraint that an agent would face in a decentralized world where there is consumption and savings. This is what a central planner would face if she were just deciding allocations optimally according to this resource constraint. Okay. So full depreciation, logarithmic utility, Cobb-Douglas production. Step 1, what do? This is the sequence. This is a sequence problem that is faced by the benevolent central planner. I don't want to solve that problem. That problem sucks. What problem do I want to solve? You want to solve the Bellman equation, the functional equation. What is that functional? What's the functional equation that corresponds to this problem? You tell me.
You substitute a control inside the.
Well, what's the first thing on the left-hand side of the Bellman equation? It's a value function. What does that value function depend on? Depends on the state. The state variable in this problem is the current value of K. We're going to eliminate the time subscript. Time subscripts don't matter in this problem because utility only depends on time indirectly through the variables C and K. The policy function is going to be time invariant. So don't start writing time subscripts down there. That always bugs me. The value function is going to be equal to what then? What's the right-hand side of the Bellman equation look like? You got to be able to do this. It's going to be the max. And what is the maximand? The principle of optimality says what? That the value of the sequence problem can be broken into two parts. The current return, which would be the log of consumption, plus the discounted continuation return. Well, what's the log of consumption? We want to substitute out C from the problem so that this is one-dimensional. What is current consumption going to be equal to? It's K to the alpha minus tomorrow's capital stock, K prime, right? The planner's choice of K prime, or KT plus 1, is the same as the planner's choice for CT. It's one decision, right? You've got resources, K to the alpha. If you decide on some KT plus 1, you've therefore made a decision on CT as well. So we're going to substitute consumption out of the problem and treat K prime, or KT plus 1, tomorrow's capital stock, as the relevant control. Plus the discounted value of the continuation return, which is what? That is the value function starting from the next period on. Function of K prime. And what does this maximization occur over? What is the choice variable? Or what is it that the planner is trying to solve for? The planner is trying to solve for K prime, which is the policy function that shows how capital maps in, KT maps into KT plus 1. And we know that it is constrained by the constraint correspondence, G of K. The planner simply can't choose any value of K prime she wants. It is constrained by the relevant constraints in the problem, which we'll talk about in just a minute. So here, K is the state, K prime is the control. And the planner would like to maximize this thing by choosing the value of the control corresponding to this optimal policy function. Now, what makes this maximization problem difficult is that the thing you're maximizing over is what you're trying to maximize in the first place. V is defined recursively here. What does the constraint correspondence look like? What are the menu of different options that the planner can choose for K prime in any given period? What's the lowest value that K prime can take? What's the highest value that K prime can take? K to the alpha. So the value of the state determines the range of possible values for K prime. K prime has to live somewhere on this closed and bounded interval. That's effectively what constrains the planner here. What we want to do is to be able to establish, without actually solving this problem, that there exists a unique, continuous, and bounded value function, V, as well as a unique policy function, pi, that shows how the values of the state determine the optimal value of the control. And we want to do it using our dynamic programming theorems. So how do we go about doing this then? To establish that the value function exists and is unique and is bounded, and that there exists a unique policy function, what we need to do is go through and see if the canonical version of the optimal growth model satisfies those set of assumptions that we worked through in the last class. If it does, then we know that those dynamic programming theorems can be directly applied to this particular problem, right? And so that's what we're going to start doing today. Now, I'm not going to go in complete order because it turns out that the most important assumption to establish, and several of them follow from that, is actually assumption 2. You guys remember what assumption 2 said? Well, I guess it had a couple of parts to it, but the most important part was that the state variable had to live on a compact subset of the reals. And when we're dealing with Euclidean space, that means one-dimensional Euclidean space. That means the capital stock has to live on a closed and bounded interval. Now you'll notice in the sequence problem, we have not imposed any constraint on K other than it can't be negative. But what we're going to have to do in order to apply the dynamic programming theorems is we're going to have to establish the fact that K, without loss of generality, actually can only exist on a closed and bounded interval. Now, even though we don't constrain K to live on a closed and bounded interval in the sequence problem, we have to show that for any feasible sequence of Ks, not just the optimal one, but for anything that the planner may choose, that K must reside on a closed and bounded interval in order to use the dynamic programming theorems. Can we establish that? Well, you know the answer. It's yes, right? If not, then what the hell are we talking about? Okay, what do we know? We know, first of all, that KT has to be greater than or equal to 0 for all t, right? So obviously there's a lower bound. Is there a natural upper bound that the capital stock can never go above? Well, let's think about that. How could we determine what the highest sustainable value of capital is in the long run? Not the optimal value of capital, but the highest possible value of capital that we could reach in the economy. Well, how would we determine that? Let's assume for the moment that we choose to eat nothing forever. our consumption is 0, then what does that imply about KT plus 1? If you go back up to the constraint here and you set CT equal to 0 forever, then what is KT plus 1 equal to? It's just equal to KT to the alpha every period. We're going to assume the constraint binds, right? This looks to me like a mapping between KT and KT plus 1. What does that mapping look like? Well, it's just the production function, right? If we start off with some initial value of capital, let's say K0, what do we know is eventually going to happen in the long run? That K will converge to some fixed point. I'm not going to say the steady state, because the steady state implies an optimal choice by the planner. This is not an optimal one. This is one where the planner says, let's pretend for a moment that I'm not going to feed any of these agents. We're just going to accumulate capital forever. Well, what's going to happen in this economy? Eventually, the capital stock is going to go to some fixed point at the intersection of K to the alpha and the 45-degree line, right? What value of K does that correspond to here? What is the fixed point of this equation? Let's call it K bar is equal to K bar to the alpha. K bar would be equal to what? 1. Okay? So if consumption were 0 forever here, eventually the capital stock would accumulate and get to 1, and then it would never change after that point. Okay? So what do we know then? If KT is less than or equal to 1, I'm sorry, if K0, I should say, is less than or equal to 1, then we know that KT will be less than or equal to 1 for all t. If our K0 is to the left of 1, we're never going to have a K that's higher than 1. What if initial capital, however, actually is bigger than 1? Then what's going to happen here? The capital stock is going to shrink until we get to this fixed point. That means KT will be less than or equal to K0 for all t. Let me define K tilde as the max of K0 or 1, whichever of the two is bigger. And we're going to assume that initial capital is finite. This implies then that K is always going to be an element of the closed and bounded interval 0 to K tilde. You see that? So the constraints on the problem, the resource constraint on the problem, suggests that the capital stock, no matter what the planner decides to do, if she decides to give 0 consumption forever or some positive level of consumption, the value of capital is always going to be greater than 0, but it can never possibly be greater than K tilde, where I've defined K tilde as the max of 1 or initial capital. That is a closed and bounded subset of the positive reals. So without loss of generality then, as I've seen that phrase before, I can impose this constraint on the problem, and it's not going to lead me to a different set of solutions, right? The sequence problem doesn't have that constraint on it. But it turns out that the capital stock is never going to exceed K tilde. So without loss of generality, I can impose this additional constraint on the problem. Therefore, the state variable here lies on a compact subset of the reals. And so that critical component of some assumption 2 is going to be satisfied. Now you'll recall that g of k was 0 comma k to the alpha. That is a non-empty value constraint correspondence, unless k is just equal to 0 forever, which it won't be. It's also continuous. So small changes in k lead to small changes in this constraint set. And it's clearly compact valued, right? It's closed and bounded for any positive value of k. The utility function is also continuous. That's obvious. We're dealing with a logarithmic utility function where c is defined on the positive reals. And we also know that the domain of u is also going to be compact, right? So what is the domain of u? So this thing that I termed xg in the last section, that's, in this case, it's all k prime pairs, which are elements of 0 k tilde times 0 k tilde, such that k prime is feasible. This is going to be a compact set, right? And so that implies then that u is bounded. So you see how all of this follows from the first part of this assumption. If we can establish that the state variable k lies on a compact set of the reals, then g is going to be compact valued. The utility function is continuous, and so u is going to be bounded. A continuous function on a compact domain is going to be bounded. The fact that u is bounded is going to directly imply then that the overall objective function has to exist and be finite as well. That was assumption 1. How are we doing so far? Y'all, this stuff is fun. Cheer up.
We got one more midterm.
I can't tell with those masks on if you're snarling at me or smiling. You're not rolling your eyes yet. Okay. All smiling?
Yeah.
Because it's so easy, or?
No, because we just like to teach you that
It's
way.
less painful than our next midterm.
Yeah.
What's your next midterm?
Econometrics on Thursday.
Ah, that's easy. OLS, x prime x inverse, x prime y. Who cares? Okay. Assumption 1. So we've already established that g is non-empty for all possible values of k between 0 and this k tilde. The other key thing we want to establish here is this: does the overall objective function here exist? That's this thing. When we substitute out consumption from the problem, we need to be left with an overall objective function that is finite, right? We don't. It doesn't make any sense for the planner to be maximizing over some infinitely valued object, right? So can we establish that this thing actually exists? Okay, that's pretty straightforward. So the value function, so that v star for the sequence problem, is a function, of course, of the initial stock of capital that the planner is endowed with. That's going to be equal to the maximized value of lifetime utility. Where the maximization occurs over this sequence of k's. Subject to kt plus 1 living on this closed and bounded interval 0 to k tilde that I defined in the last page with initial capital given. So it's super straightforward, I think, to establish that this thing is, that the overall objective function exists. And that is, by the way, just to make this clear, or clearer, we want to show that this thing exists for any feasible sequence of k's, not just the optimal sequence, okay? So how do we do that? Well, first you need to recognize that let's take the period utility function, log of kt to the alpha minus kt plus 1. We know that that is bounded above by the log of kt to the alpha. Why do we know that? Because kt plus 1 has to be bigger than or equal to 0, right? So we're subtracting something that's positive from the log, so it's bounded above by the log of kt to the alpha. Well, this is, of course, equal to alpha log of kt, right? Well, what is the log of kt bounded above by? What the hell did we just do for assumption 2? We just determined that the biggest possible value that k can take is this k tilde. So this is bounded above by alpha log k tilde, which has to be finite because it's on it's a compact set on the real line. This implies then that v star of k0 has to be less than or equal to the sum from 0 to infinity, beta to the t, times this alpha log of k tilde. If the period utility function is bounded above by alpha log of k tilde, it can't possibly be bigger than that, then the maximized value of lifetime utility has to be bounded above by the discounted value of that over time, which, if you know your geometric sequences, right, that's just going to be what? Alpha over 1 minus beta times log of k tilde, which is less than infinity. So we can bound the value of the lifetime utility function for any feasible sequence of k's, not just the optimal one, by recognizing essentially that the utility function itself is bounded because it is continuous and defined on a compact domain. So we verified then basically assumptions 1 and 2. That's enough to establish what? Let's see how much you guys remember from the last class. Assumptions 1 and 2 are sufficient to give us what?
Principle of optimality.
Equivalence of values. So the sequence problem and the Bellman equation achieve the same value. The principle of optimality, meaning that the value function can be written as the current return plus the discounted value of the continuation return. And theorem 2 also establishes that some optimal plan exists, right? And that the value function itself is unique, continuous, and bounded. So what we know already is that there has to exist a unique value function, v, that maps elements of the reals into the reals. The Bellman equation is unique. And we know that some optimal plan exists, which if we pursue it forever, will obtain v in the long run. Now, what more do we need to establish the existence of a unique optimal plan or an optimal policy function? We need to establish what? That the value function is strictly concave. That's going to follow from the concavity of the utility function and the convexity of the constraint correspondence. That's where I'll start in the next class. So we'll move on to those assumptions, and in the next class, we'll go through the rest of them. It shouldn't take too long. And then what I want to spend the bulk of the time doing is showing you how to solve for the policy function analytically in this particular class of models. And it requires employing a technique in order to solve a functional equation, which is the method of undetermined coefficients, or a guess and verify strategy. So that's what we'll do for the most part of the next class, is finish going through the assumptions necessary to establish all of those key theorems in dynamic programming that we can apply to the canonical optimal growth model. And then I'll show you the techniques for actually solving for the policy function analytically, right? That is, we're looking for this thing, right? So kt plus 1 is some time invariant function of kt. Well, what does the function pi look like? Can we solve for that thing explicitly? We could solve for it explicitly in a solo model. We could solve for it explicitly in some versions of the OLG model, like the one on your test. You could solve for it explicitly. Hopefully you did. I don't know. And you can solve for it in the canonical optimal growth model. That is one that has logarithmic preferences, Cobb-Douglas production, and full depreciation of capital. In fact, if I'm not mistaken, on your test problem, we assumed full depreciation of capital. And that helps in solving for the optimal mapping from KT to KT plus 1 in that problem, where you had workers working in both periods of their lives. Okay, y'all have any questions about that? I'm going to finish a couple minutes early, actually, because I think it'll take more than 10 minutes to go through the next assumption. No? Good.